You know that really specific frustration you get when you're on the phone with an automated customer service line.
Oh, I know it well.
You start off so hopeful. You say something simple like, "I'd like to check my balance."
And it works. The voice says, okay, checking your balance.
And you think, "Wow, this is it. We're actually living in the future."
It's the honeymoon phase.
Exactly. But then you get a little too confident. You say, "Actually, wait, did that check from Tuesday clear yet?" And you just get this dead silence for 3 seconds. And then the cheerful voice comes back and says, "I can help you with checking or savings. Which would you like?"
The dreaded loop.
Yeah.
You went off script and the machine it panicked.
It feels like the system is a genius 1 second and then completely unbelievably stupid the next.
Right. It's this illusion of simplicity. And that moment, the until it falls apart moment, that's actually the most interesting place to start. Because underneath that smooth synthetic voice is what computer scientists call a Rube Goldberg machine of complexity. And today, we are tearing that machine apart.
We're doing a deep dive into spoken language dialogue systems. And for this, we have a really fascinating set of materials. It's a foundational chapter by Robert Dale from 2011.
And crucially, a retrospective he wrote a decade later.
So it's basically a before and after picture of a tech revolution.
It really is. It's a snapshot of how we used to build these things, the hard manual way, and how the world of, Siri and Alexa completely upended the chessboard.
Okay, so let's define the scope here. When we say spoken language dialogue systems, what are we actually talking about? Is it just chatbots?
It's surprisingly specific. We aren't talking about the old Eliza chatbots from the 60s, which were just text pattern matching.
Right.
And we aren't talking about a simple Google search where you ask one question and get one answer back.
So not just Q&A.
Exactly. We're talking about multi-turn, goal-oriented conversation where voice is the main channel. You say something, the machine replies, and this is the kicker. It has to remember what you said 10 seconds ago.
The source material highlights this massive tension right away. People assume you can just, glue a microphone onto a text chat bot and you're done. Why? Why doesn't that work?
Because speech is just fundamentally messy. In text, the input is clean. It's perfect data.
The letters are the letters.
Right. But in speech, the input is just a sound wave. It's full of background noise, accents, ums and ahs, and just uncertainty.
So you're dealing with the probability of a word, not the word itself.
Exactly. And if you build a system assuming the input is perfect, it just crashes the second it meets reality.
So let's look under the hood. In that classic 2011 view Dale describes, how did they solve this? The architecture sounds less like a single brain and more like a relay race.
That is the perfect analogy. It's a pipeline. 5 distinct runners passing a baton.
And if any runner drops it,
the race is over, the whole thing fails.
Okay, so let's walk through it. Runner number 1 is speech recognition.
Right. ASR. Its only job is to take sound waves and turn them into a string of words. It doesn't know what the words mean.
It's just a stenographer. It types what it thinks it heard.
Precisely. Then it passes the baton to NLU, natural language understanding.
Okay, and what's NLU's job?
NLU is the interpreter. It looks at that string of words and tries to extract the actual meaning, the intent.
So now we know the user wants to book a flight to Boston. Who decides what to do next?
That's the third runner, the dialogue manager. This is the brain of the operation.
The one in charge.
Right. It looks at the meaning and decides the action. It thinks, okay, the user wants Boston. Do I have a date? No. Okay, my next move is to ask for a date.
And once it decides what to say, it passes it to
natural language generation to formulate the sentence, and then finally speech synthesis to turn that text back into sound for you to hear. 5 steps.
And the delay must be a huge issue. If the dialogue manager takes too long to think, you assume the call dropped.
Latency is a killer, yeah. But the bigger problem is error propagation. It's like a game of telephone. If the first runner hears Austin instead of Boston, the whole team runs the wrong race. You end up with a flight to Texas.
This brings us to what I thought was a really compelling part of the reading, the Great Divide. It describes these 2 parallel worlds of development.
The commercial world and the research world.
They had totally different goals, didn't they?
Completely. Think of it as a train on a track versus an off-road vehicle.
The commercial systems, the banks, the airlines, they're the trains.
Yes. They're the pragmatists. Their goal isn't to be cool or natural. It's to be reliable, cheap, and efficient. You can't have misunderstandings with a bank transfer.
So how do they guarantee that reliability?
They use something called finite state grammars. It's basically a giant, rigid flowchart. The system says checking or savings, and it is literally only programmed to listen for those two words.
It's wearing blinders.
Intentionally. It ignores everything else. If you go off that script, it hits a wall. We call this system-directed dialogue. The machine is the boss.
It interrogates you. That's why it feels so robotic.
Exactly. But then you have the research world. The explorers. They wanted mixed initiative systems.
Meaning the user can take the lead.
Right. In a mixed initiative system, you could just say, I want to fly to Boston next Tuesday. The system uses a frame-based approach. Imagine a form with slots for destination and date.
So it hears that one sentence, and it fills in both the Boston slot and the Tuesday slot at the same time.
Exactly. It just looks at its form, sees what's missing, and only asks for that.
That sounds so much better. Why didn't everyone just use that?
Because it's so much riskier. To do that, you have to use statistical models that allow for a huge vocabulary. You're letting the user say anything.
And when the user can say anything, the chance of misunderstanding just skyrockets.
Right. So the trade-off was freedom versus reliability. For a long, long time, the rigid commercial systems were the only ones that actually worked well enough to sell.
Let's dig into the brain of those research systems, the dialogue manager. The source talks about dialogue acts. I'd never really thought about conversation that way.
It's a linguistic view that changes everything. We think we're just exchanging information, but every single thing we say is an action.
Give me an example of an act.
Well, if I just say, okay, what does that mean? Am I agreeing with you? Am I just signaling that I heard you, like a nod?
Or are you trying to end the conversation?
Right. The system has to classify that, okay, into a specific dialogue act like confirm or acknowledge to know what its next move should be.
So it's constantly tagging everything. This is a question. This is a confirmation.
It is, but the real magic is how it tracks the conversation. We talked about the rigid flowchart, but the research world moved to information state approaches.
This is where it gets a little sci-fi.
A little. The system tries to maintain a mental model. What do I know? What does the user know? What if we both agreed on?
And the ultimate version of this is the POMDP.
The partially observable Markov decision process.
It sounds like a secret government project. Break that down for us.
Think of it like walking through a room in the dark. You can't see exactly where you are. That's the partially observable part.
Okay.
You take a step. You think you moved 3 feet, but maybe you only moved 1. A POMDP system is never 100% sure what you said.
So it doesn't just store one fact, like he said Boston.
No. It stores a probability distribution. It thinks there's a 70% chance he said Boston and a 30% chance he said Austin.
So instead of just guessing one and hoping for the best, it holds both possibilities in its head at the same time.
Yes. And its next move is based on that uncertainty. If it's 99% sure, it'll just book the flight. If it's only 60% sure, the math tells it the risk is too high.
So it asks a clarifying question. Did you say Boston?
Exactly. It's surprisingly human. I feel like I do that in a noisy bar all the time. I'm running a little POMDP in my head.
That's a perfect lead into the human element, because we humans are.
Yeah.
We're weird speakers. We don't use perfect sentences.
We are a total nightmare for computers. 2 big concepts from the source here are incrementality and grounding.
Let's start with incrementality. That's about when we understand things, right?
Right. Older systems worked in batch mode. They'd wait for you to finish your whole sentence, then start thinking. But humans process word by word. If I say, pick up the red, your brain is already scanning for red things before you even finish the sentence.
You're narrowing down the possibilities in real time.
You are. And if a machine can do that, it allows for something really important. Back channels.
Back channels, what are those?
Those are the little noises we make. Right. Yeah.
The conversational nods.
Yes. A system that can process incrementally can drop an into the middle of your sentence. It proves it's listening. It makes the interaction feel alive.
Which connects to the next concept, grounding. I love this idea. It's about how we confirm we're on the same page.
Grounding is the social contract of conversation. We have to constantly establish a shared understanding, a common ground.
But we don't do it explicitly. We don't say, I have now stored that fact.
No, we do it implicitly. If you say, I'm going to Paris, and I say France or Texas, I am checking our common ground.
Or if I just say, great, and move on, That's also a grounding move.
It is. And machines are historically awful at this. They either assume they heard you perfectly and booked the wrong flight.
Or they ask for confirmation on everything. Did you say Paris?
Yes.
Did you say Tuesday? Yes.
Exactly. A total failure of grounding strategy. But the biggest failure is when the system just gets it flat out wrong. The nemesis, error.
The source has a great example of this with disfluencies. The pizza order. Can I have a mushroom? No, wait, a chicken pizza.
To a computer, that sentence is a logical bomb. It hears mushroom, no wait chicken.
Yeah.
It has to realize that no wait is an edit command and chicken replaces mushroom.
We do that effortlessly.
But for a machine, it's incredibly hard. How does it cope?
Confidence scores.
Right, the recognizer attached as a score. I'm 80% confident this is what they said. If the score drops below a certain threshold,
It triggers a repair. Sorry, I didn't catch that.
or you get the nuclear option, the generic spoken command vocabulary.
This was a dark time.
It really was. The engineers basically gave up and said, humans are too messy. We'll force them to speak like computers. User, initiate sequence.
It's the military approach.
Yeah.
And it failed miserably because people just hate being told how to talk.
Completely. So that was the world in 2011. A war between rigid commercial systems and fragile research models, all drowning in error.
But then we get to the postscript.
The plot twist.
Robert Dale comes back 10 years later and basically says, everything I just told you, it's history now.
The ground shifted under everyone's feet around 2015. The catalyst was the smartphone. Siri, Alexa, Google Assistant.
Everyone suddenly had a high-quality microphone in their pocket.
But it wasn't just about usage. The technology underneath had a revolution. We entered the deep learning era.
We moved from the relay race
to the end-to-end model.
Explain that. What happened to our 5 runners in the race?
They started to merge into one. Instead of having teams of engineers hand-coding grammar rules, we started using these massive neural networks.
So you just feed it data.
You feed it millions of examples of audio on one end and the correct response on the other, and you let the network figure out all the messy steps in the middle.
The machine teaches itself the rules.
It learns patterns far too complex for any human to write down, and a huge part of this was a breakthrough called word embeddings.
That's a term you hear all the time now. What does it actually mean?
In the old days, to a computer, words were just symbols, the letters B, A, and K. The computer had no idea that bank was related to money.
It was just a barcode.
Exactly. Word embeddings turn words into coordinates on a vast, multidimensional map of language. On this map, the system learns that the word king is mathematically close to queen.
So the computer can literally do math on meaning.
Yes. So if you say, I need some cash, and the system has never heard that exact phrase, it can look at its map and see that cash is right next to money in bank. It understands your intent without needing a keyword match.
It changes everything. That kills the old flowchart model.
It absolutely destroys it. Recognition error rates just plummeted. We're not fighting just to hear the words anymore. The machine has a decent shot at understanding the concept.
It is amazing to think that happened in just about a decade. We went from, please, say yes or no, to just rambling at the smart speaker on the counter.
It's all about the power of data. The old systems were brittle because they were data-starved. The new ones are fluid because they're data-rich. They've heard billions of conversations.
So as we wrap up this deep dive, we've gone from this illusion of simplicity through that complex relay race and landed here in the age of deep learning. But there's a final thought in the source material that I found really provocative.
The Ballantyne quote.
Yeah. It's better to be a good machine than a bad person.
It hits hard. For decades, the goal of all this research was naturalness. We wanted the computer to sound human, to say, and uh-huh.
We wanted to pass the Turing test.
But Ballantyne's point is, maybe that's the wrong goal. If I'm booking a flight, do I want a chatty friend who might make a mistake, or do I just want a hyper-efficient tool?
As they get better and better at mimicking us, we have to ask, are we making better interfaces, or are we just making them better liars?
That's the uncanny valley, but for conversation. When a machine pretends to be a person, we expect it to understand like a person.
And when it inevitably fails, we get so much angrier than if it had just acted like a robot from the start.
Right. You forgive a toaster for burning your toast. You don't forgive a person for ignoring you.
So when the machine pretends to be a person, it invites that social judgment.
Maybe the future isn't about creating a digital buddy. Maybe it's about creating a machine that is unashamedly a machine. Just a really, really good one.
And that is the open question. We now have the technology to mimic humanity. The real question is whether we should use it or just focus on getting the job done.
I think I'm on Team Toaster. I just want it to work.
Glasgow. I think I am too. A huge thank you to Robert Dale for the incredible source material. It's so rare to get that kind of clear view from someone who was there for both eras of a revolution.
Absolutely. It's a classic text for a reason.
And thank you for listening to this deep dive. Hopefully the next time you find yourself yelling at a customer service bot, you'll have a little more sympathy for the POMDP that's trying to figure out what you mean.
Or at least you'll know why it's ignoring you.
Exactly.
Dave?
For now.